Voronoi diagrams. And soft means, very roughly, basically what you can compute numerically and yet get certain guaranteed combinatorial properties correctly. So that's roughly what soft means. I'll use the word soft a lot. Okay, I think I'll begin by introducing the problem and saying what's the difficulty or why do we want to do soft things when in some sense, well, at least for some of the problems, we can do it exactly, in a hard way. Why do we want to do that? And then how do we actually do it if we want to do it softly? And as usual, soft approaches have conditions. It's very common in numerical computing to say assuming smooth, assuming non-singularity, and all kinds of conditions, because numerics cannot deal with the singularities. And so we have to talk about conditions. And in the last part, I don't think I'll have much time to go over it. I'll talk about the unconditional approach. How can we do it unconditionally, in a sense? That is, no matter what the input is, even if the input is degenerate, we want to compute something that is guaranteed. Okay. So this talk I thought would be great for this seminar, because this seminar is symbolic-numeric computing seminar. And of course, we understand symbolic really means algebraic in a general sense. And of course, algebraic numbers is the prime example of that kind of exact computing that we're interested in. Algebra and the algebraic systems are somehow underlying all the exact computation. And of course, there's many wonderful things we all love in the algebraic viewpoint, and in some sense, when you do numerical computing with real numbers, when you do geometry, the real RAM model is the default assumption, and that captures the algebraic viewpoint exactly. It's exact, no errors. And on the other hand, there's the numeric approach, which is approximate, and is usually a posteriori correct. It says, well, assuming that the error bound are not too bad, actually this is the correct output, but we don't guarantee it during the algorithm. At the end, you might get nonsense, but that's because the error went off the wall. And as computer science people, we don't like that. And the dilemma is that the numeric approach, despite all these problems, are hugely successful. Last summer, I ran this conference called ICMS, International Congress for Mathematical Software, and Nick Trefatton was one of our invited speakers. And most of the people in the audience were algebraic computing people, computer algebra people. And Nick said, for every one of you here, there are 10,000 of us out there. And he's right. So why is that? And despite the growing power of algebraic systems like Maple and so on, it's still MATLAB that dominates. And a hint about that, I mean, there are many hints, there are many reasons. Today I'll give some of the reasons. The hint is, in some sense, there's a quote that I love from, I think, who was it? Who says, algebra is generous. It gives you a lot more than what you ask for, very often. For instance, singularities, if you view it from an algebraic viewpoint, ideal theoretic viewpoint, it gives you a lot of information. But if you're doing numerically, you just need to know that there's a singularity. That doesn't matter what the structure of the singularity is. So it's very generous, and you pay the price for that generosity. And of course, to me, I've been working on exact computation for quite a number of years. And in exact computation in geometry, you have to do things numerically, but you cannot escape what I call a zero problem. Deciding zero, whether a real number is zero or not. You can approximate it to whatever precision you like, and that's a given that you can do that. But you cannot decide zero without additional algebraic data. And for many problems, algebraic problems, we can do that, but in general, we don't know how to do that. So that's a zero problem. And there's a quote here by Dan Richardson, who did a lot of work on basic work on zero recognition problem. He says, the history of the zero recognition problem is somewhat confused by the fact that many people do not recognize it's a problem at all. But it's really lurking in there. in some sense, that underlies what I'm going to talk about. So let me go to my topic today, which is about Voronoi diagram. And so here's a very nice example of a Voronoi diagram, very easy to understand. The input is a set of points in 2 dimensions, and you output this structure, this cellular structure called a Voronoi diagram, which you can think of as a graph, if you like, with Voronoi vertices and Voronoi edges. And the edges here are all straight lines, very simple. You can generalize this in many, many ways. Here's one generalization. Suppose instead of points, you have polygons. And think of this as polygonal sets. And the Voronoi diagram are these red curves that you see. So they're no longer straight lines, they're parabolas and straight lines. Yes, question?
What's that line, red line going
This one? Yeah, this is a self-Voronoi diagram because it is, Voronoi diagram is the set of all points which are equidistant to at least 2 points on the obstacle set. And every point along here is closest to this, some point on this edge and also on this edge. Although those 2 came from the same polygon and you might like to eliminate that, you could. But certainly it is important information that might be used for some application. You can delete it if you want. And what we're interested in this talk is about what I call subdivision approach. And you can, it's very intuitive. I take an initial box, I keep subdividing it. And in some sense, the gray boxes are those boxes where the Voronoi edge passes. And I'm going to approximate it. I'm only interested in approximating it to whatever precision. And I'll just, if I know it passes through this, I put a vertex in the center of this edge and in the center of this edge and connect by a straight line. Okay? And if the boxes are small enough, you'll go to the arbitrarily good approximation.
The white boxes are remnants of quad tree construction.
What's that?
Am I right? That white boxes are remnants of the quad tree construction.
That's right. It's all remnants of a tree construction. And in fact, this curve is computed using exactly the same method, except we force the thing to go down to higher resolution. So you can get arbitrarily good approximation that way. Here's the same thing for 200 random triangles. And here is a case where you have just 2 infinite lines, these blue lines, but and the surface, Voronoi surface separating the 2 is this quadric surface. And this is sort of truncated so that it's visually, I think it's truncated by some kind of sphere so that you can see it. And this case will be very important for this talk. So, and then there are lots of generalizations. People keep inventing new ones. Here's an area called centroidal Voronoi diagram in architecture. I won't even go into that. There are conferences and journals devoted just to Voronoi diagrams. And this is actually just for picture only. That's not what I'm going to talk about. It's a very different notion of what I will be talking about. So what is a Voronoi diagram? And for this talk, to me, I will consider Voronoi diagram of omega, and omega will be the same variable I'll use throughout the talk. It is a subset of RD, and D is 2, 2 and 3 in this talk. It's a polyhedral set, so the boundary are all linear, piecewise linear. And of course, you can define what is called a Voronoi set in the sense of any point is said to be on the Voronoi diagram in this Voronoi set if you take the largest ball center at that point so that it touches 2 or more points of omega. And that's said to be on the Voronoi. So it's a set of points. So this, I write Vo with a bar here, is a subset of this. You can talk about that, but of course, when you want to compute, this set has a lot of structure. It has a structure of a simplicial complex, for instance, generally. And so really what we want to compute is this complex, which I denote by Vo without the bar, okay? This is our problem. So it's a simplicial complex in which this set has been broken up into zero-dimensional simplices, which are points, curves, one-dimensional simplex, and two-dimensional surfaces, and so on, up to D minus 1. So the goal is to compute a simplicial complex that is, we can't really compute this directly because in general it would be algebraic curves and so on. We want to only compute an epsilon approximation. So usually the curves will be approximated by, say, polygonal lines. And the surfaces, the surfaces will be represented by triangulation, for instance. Okay? But they can be arbitrarily approximated. So this is our goal. All right? Any questions? Okay. I assume these are basic things that you can guess. So what is the difficulty? So I call this a Voronoi quest, 20-year-old quest. We're going to compute the Voronoi diagram of a polyhedral set in 3D. That's all. So, whoa. This is a lot of applications. There's a lot of interest in it. It's not because nobody is interested in computing. That's why we haven't computed it. But we don't have an algorithm. How can that be? I'll try to hope to show you why it's a stumbling block. Those of you who are familiar with computer algebra and cylindrical algebraic decomposition, you know right away this is computable, right? It's just cylindrical algebraic. That's a sort of sledgehammer algorithm that will solve everything that's algebraic. You'll certainly solve this problem, but nobody considers that as a solution to this problem. We want a direct algorithm, and nobody has figured out what the direct algorithm is. That's the open problem. In 2D, I actually give the first n log n algorithm for it. And it can be done, and it's not difficult. We understand exactly everything there. In 3D, it's open, and I just give some 2 early papers that try to do this. And a few years ago, 2010, a paper by Hammer, Setter, and Halprin gave an algorithm for constructing the exact Voronoi diagram of lines in 3D, arbitrary lines, infinite lines in 3D. Okay? So it's a special case of our Voronoi quest, just a special case. And they call it a major milestone. Why? Because it's the most interesting problem solved so far for this general problem, even though it's a special case. Of course, there's a trivial case, which is just points in 3-dimensional space. That's all trivial. We know how to do that in every dimension. Not just 3D, that's polyhedra. But this is always the major milestone. So what's the difficulty? So let me just very briefly recap how one would go about computing the exact Voronoi diagram. So I say that input is omega. And omega is a polyhedral set. So if you look at the boundary of omega, it can be decomposed into triangles, edges, and points, okay? So we call them features, boundary features. We call them corners, edges, and walls. So here's a picture. W is a wall, A, B, C are corners, and E, F, G are edges. These are features. And any pair of features will determine a Voronoi surface, which is simultaneously comprising all the points which are simultaneously closest to those 2 features. So if you have a corner, you have a corner feature. That's very easy. You have 2 points, then the Voronoi surface is just a hyperplane separating those 2 points. It's like very simple. And similarly, you have 2 walls, 2 infinite walls in 3D. It's 2 intersecting planes going through the intersection point and so on. So you have corner, or point, edge. The most interesting is edge, right? 2 edges. And if you assume the edge goes to infinity, there become two lines. And that's exactly the picture here that you saw earlier. And this, of course, is the case that was solved in the major milestone. So they use that algorithm to compute this. You can see this surface, right? It's some kind of subtle surface, quadric surface. And, well, in 3D, we have surfaces, we also have curves. So the curves are defined by 3 features. So you have corner, edge, corner, wall, and so on. 10 of them. Again, the most interesting are 3 edges. And again, to make it simple, the edges are finite, so you have to determine the endpoints of the thing to know the limits of that if you want to compute a Voronoi diagram of 3 edges. But let's make it infinite lines to make it simpler, to avoid that difficulty. Well, not difficulty, the special case you have to worry about if you were computing it. So roughly speaking, the since I said these surfaces are quadric surfaces, just degree 2, very easy to understand, we know all about them. These curves are intersections of 2 quadrics, so it's a quartic curve in 3-dimensional space, a space curve, okay? In general. Why? Because they're degeneracies. So there's a theorem, and it's because of this theorem that the paper in 2010 was able to solve the algorithm. This theorem from Everett et al. Tells us what is the nature of the Voronoi curve determined by 3 lines in space. The first case, there are about 5 cases down here, I haven't shown you yet, is that it's a non-singular quartic curve if the 3 lines are pairwise skewed and not all parallel to a common plane and not lying on the surface of a hyperboloid of revolution. So hyperboloid of revolution, something like that. You might have 3 lines all lying on that surface. That's very special. But if that's not the case, then you get a non-singular curve, which is quartic curve. Well, there are other degeneracy. If the 3 lines are pairwise skewed, but they lie on the surface of hyperbola of revolution, then what you get is 2 components. The curve now has 2 components. It's a cubic and a line. A cubic curve and a line. And otherwise, if the 3 lines are pairwise skewed and all parallel to a common plane, like maybe this is the plane, the table, and you have 1 line here, another line here, and another line here. They're all pairwise, they are skewed, but they all happen to be parallel to this plane. So in that special situation, the Voronoi curve is a nodal quartic. So there's a singularity somewhere. And otherwise, if there's 1 pair of coplanar lines, a coplanar line is either 2 lines which are parallel or 2 lines that actually intersect. They lie in a plane if they intersect. Then it is 1 or 2 parabolas or hyperbolas. And finally, if there are 2 pairs of coplanar lines, then it's this. So this is the complete theorem. This is a complete classification. Now think about it. If you are trying to compute a Voronoi diagram of 3 lines, you have to distinguish all these cases. And until you have this theorem, you don't know what to do. Right? So my point is that all exact algorithms must distinguish these cases, and you better prove a theorem like this before you do this. So the larger moral of this story is that exact computation is hard because exact computation forces you to recognize all these degeneracies. You must understand all the degeneracies. And to decide degeneracy is deciding 0. All these are predicates. You have to check, is this polynomial expression 0? If it's 0, then a degeneracy happened. And numerically, that may be hard to do. That's a 0 problem showing up. Very bad. Outside of this context, you can imagine there are other problems for which we don't even know, in principle, whether we can do exact computation. It may be impossible or unknown to be. Nobody knows whether it's possible. Several years ago, I wrote a paper in SOCG where we proved that the problem of trying to find the shortest path, suppose this is a planar problem. If I give you a set of circles and I want to go from a point A to a point B, I want the shortest path. So maybe the shortest path is this one. Or it might be, this one, or it might be this one, something like that. So combinatorially, you can construct the graph of these common tangents, right? divided by n squared of this, and it's a straight line graph with a straight line, circular arc, straight line, circular arc. And you can construct this order n squared graph and compute using Dijkstra's algorithm because all the distances are positive. N squared algorithm, right? N squared log n. We actually wrote our paper is called "This Problem, Shortest Path Amidst This Obstacle is Decidable." What is coming up? Why do we say it's decidable? It's all, even polynomial time, right? The problem is when you do Dijkstra's algorithm, you have to compute these distances and you have to compare and see who is bigger. And these distances, well, let's assume that input are algebraic or even rational. And these tangent points are algebraic points, they involve square roots. So these distances are all algebraic numbers, but these arcs are transcendental. And you have to add up these arcs. And you can approximately do whatever precision you want, but if they're really equal, how do you know to stop? There's a stopping problem. The halting problem is, I call this the numerical halting problem. If you can't solve this, you cannot solve this problem on a Turing machine. Right? So we actually give a solution without any bounds, so it's decidable. But if you know a little bit more about transcendental number theory, you can actually get some bounds, and you can prove this exponential time. Okay. So this is a planar problem. So we can imagine much harder problems. And if you just generalize this a little bit from circular disk to elliptic disk, then as far as I know, we don't know if it's decidable. I think it is, but it's much harder theory lurking underneath you have to appeal to. So that's not known, for instance, if you use elliptic obstacles. So the good thing is that most applications don't need exact computation. For instance, these days I've been going back to motion planning, but without the exactness, I want soft methods. So clearly in motion planning, you should never use exact methods. All physical constants are known up to about 8 digits of accuracy. That's it. I think the gravitational constant is only known up to 3 digits. So why do you need infinite precision in physics? Anything physical, mechanical, you cannot control robot to that accuracy. So that's why we should be looking at soft methods, which are numerical. That's what the numerical people do, except they don't guarantee things. That's what we have to do. So how do you compute soft Voronoi diagrams? Softly. So I'm going to describe a very simple framework. All of you have some intuition about how to do this in this framework. So let me make sure we know what the input is. The input is omega, which is this omega here, which is the polygonal set in 2D or polyhedral set in 3D. A box, meaning I want to compute a Voronoi diagram restricted to some region. So box B0. So if you have obstacles here, and you want to compute Voronoi diagram, you're just interested in what is truncated, limited to that box. So not a global method, but local. That's it. The other thing, numerical methods tend to be local. Algebraic method tends to be global. If you use algebraic method, somehow you have to know about all the singularities everywhere, not just where you're interested in. You pay a price for that. And I give you epsilon. And we want to compute an epsilon approximation of the Voronoi diagram, which is this. Let me draw it in blue. I want to compute some epsilon approximation to that, restricted to B. So here's the example. This is the Voronoi diagram, and this is our approximation. And the framework is what we call the subdivision framework. So the input is omega, B0, and epsilon. The output is some kind of graph. For 2D, it's a graph. Combinatorial graph. There's an epsilon approximation of that. not just a graph, of course, it's a graph of embedded in the plane. An embedded graph. So we initialize a Q, input Q, to just the box B0, and then we keep subdividing. We just take a box out from the Q, input Q, split it into 4, do some classification, and either put some of it out to the output Q or put it back in the input Q. And you keep doing this until the input Q is empty, right? You just keep splitting until you reach empty. And now when you stop, then all the boxes are here. So that's the subdivision phase. And then usually there's a need to regularize. A very simple idea for regularization is to make sure that all the boxes which are adjacent to each other differ by a depth of at most 1. So if you have like this box and this box differ by a depth of 2. So that's no good. So you're forced to split this guy. Now you're okay. Now this box and this box, they differ by a depth of 1. So it's a way to clean up things up a little bit, because usually that's needed in order to do construction.
Those are only for the boxes in Q out, right?
What's that?
Those are only for the boxes in Q out, right?
Right. This regularize is only for the boxes in Q right.
Yeah,
But
okay.
all the boxes in Q input has already been sort of split up and put into Q out already.
Alright.
Actually, some boxes might be thrown away.
Yeah. That's
Yeah,
what I was thinking.
that you can some throw away, and regularization is only for the boxes that are still in your Q output. Some has been thrown away. You actually don't care about those anymore. And finally, if everything is done, if your decision to do subdivision regularization has enough, sort of stops only when there's enough information to figure out what's going on, you can now do the construction. And I hope you all know about what is called the marching cube, which is a favorite of a lot of people who do a lot of computing out there. It's probably one of the most widely used algorithms out there. Marching cube idea is, suppose you want to approximate a curve. This curve is f equals 0, f of xy equals 0. So here's the curve. And you subdivide until it's small enough somehow, and then you evaluate the function curve here. It says f is positive here, f is negative here, f is positive here, f is negative here. You say, oh, the curve passes through here, like this. This is called marching cube. You label the edges. And what we're doing actually in some sense is a generalization of this. Of course, marching cube is notorious. It doesn't guarantee the correct topology. They usually go down to epsilon and then they do the construction. For instance, a very simple example is, what if the sign here is positive, negative, positive, negative? So you say, well, the curve passes through here, here, here. Usually we just put a point right in the center. And say, okay, the curve passes through these 4 points. Now you have to connect them. How do you connect them? Well, you can connect them this way, or you can connect them this way, or you can connect them this way, right? And topologically, you can get completely different answers. And then usually there's a refinement stage. You want to get down to epsilon, you do this. But usually we're not too interested in that. Once we get a correct topology, we stop. We don't even go further. But you could if you want to. So everybody understands this framework. This is the kind of algorithm I'm interested in developing. Okay? So what I want to point out is that most people in theoretical computer science don't work on this class of algorithms. Why? Because it's not the real RAM model at all. We've moved out the real RAM model. And the methods are local in some sense, as I tried to emphasize earlier. And it's possible to be numerical rather than algebraic. You see, but even in the subdivision method, you can do things exactly. For instance, root isolation. You can do root isolation by subdividing the, say, complex plane and use stem sequences, generalizations of stem sequences that count roots. That's exact. But you probably shouldn't do exact methods for this framework, for most applications. For instance, what we have been doing root isolation for a while, and we've been using numeric. It's much better than the exact methods, much better. And there's a very simple reason why that's a bad way to do stem sequences, to count how many times the complex curve cuts an edge, because you're not interested in that edge. You're not interested in the topology of that edge. So why spend all the effort to figure out exactly how many times it cuts it? So it's an overkill. And therefore, such algorithms will never compete with the purely numerical kind of things that we do. So as I said, we have used this kind of framework for approximating curves and surfaces, for root isolation, for real, complex, and even analytic. Because all these methods can be done analytically. It doesn't have to be algebraic at all. And in these two cases, one can prove that our results are actually asymptotically up to logarithmic terms. The size of the tree is actually as good as, say, stem sequence, the exact method. So that's a bit surprising. I think I don't have time to do demo. Well, actually, I'm not using my laptop, so I can't do the demo. I was going to use my laptop and use a demo of these kinds of algorithms. So for Voronoi diagram, as I just want, you don't have to look at it in detail, just to say that there's, obviously people have done this before, Voronoi diagram. And I just want to show, the first paper is probably the one in 1992 by Lavender et al. So what is new? What is new? As I said, subdivision is very old. It's the obvious thing. Practitioners can just do it, roughly. I think what is new is our attempt to be rigorous. And one idea that I want to emphasize is what I call resolution exactness, or epsilon exactness. And epsilon is what I call the resolution parameter. And for any problem you want to solve, you can always introduce an epsilon parameter, right? The question is, how do you use this epsilon parameter? And I want to say there's a good way, a right way and a wrong way to use it. And I'll illustrate it by our work in from motion planning. To use epsilon correctly, let's consider the motion planning problem, where you're given an input obstacle set and you're given the robot configuration, starting and goal configuration, and you ask, is there a path to get from this initial to the goal configuration for the robot? Okay? It's either yes or no. Now, there are exact algorithms to solve this. It's a purely algebraic problem in some sense. So in principle, it can be done, but are there good methods for doing that? And suppose we only want to do approximation. Because if you want to do exact algorithms, as far as I know, there are no exact algorithms in 3D, except for trivial cases or points. For the same reason, we don't know how to compute Voronoi diagrams for 3D. There are too many degeneracies. We don't understand how to do that. So here's the correct way to use epsilon. If your algorithm has a constant k, I don't care what the k is, as long as it's positive, greater than 1, such that if there is a path of clearance, clearance is the closest you get to the obstacles, the robot path. There's a point at which it's closest to the obstacle. That's the clearance. Of course, the clearance must always be positive for that to be called a path. If the clearance is at least k epsilon, then you better say yes. And if there's no path of clearance epsilon divided by k, you better say no. Okay? So say k is equal to 2. If there's a clearance of 2 epsilon, you must say yes. If there's no clearance of epsilon over 2, you must say no. In other words, this gives you a bit of safety. It says that don't say yes answer if you're too close to the obstacle. And physically, it makes a lot of sense. Since we cannot control robots to very high precision, we want some safety. But notice something about these two conditions, though. There's a gap. What happens if your clearance, if the best clearance is between in this gap, what do? I don't care. If you're lucky enough to find a path, say yes. Show me the path, say yes. Otherwise, you can say no. Both are correct. Okay? So such kinds of algorithms are indeterminate. Even though input is deterministic, the whole problem is the deterministic problem. You're computing, in some sense, your approximation introduces an indeterminacy. Well, you may say you don't like such algorithms. Okay, too bad. But I believe they're very good. It's a good price to pay for this. And you can sort of see that such algorithms allow us to solve this problem by numerical means. There's no need to decide zero. Never. Or you shouldn't. You shouldn't try to decide zero. So to summarize, if you use epsilon correctly, like for the example I gave there, it allows us to avoid the zero problem. And if you're computing geometry, it provides a simplified, non-degenerate geometry. You can avoid degeneracies. Degeneracies are very hard to understand, in 3D especially. Even for polygonal objects, degeneracies are usually out of our ability to analyze easily. And it also means that you can use purely numeric primitives to solve the problem. You don't need algebra.
Is it a question?
Yeah.
What's like the difference versus just saying if a number is close to zero, then output maybe?
Right. That's true. Except that you have to decide what close to zero means, and the algorithm has to do a lot of decisions.
If it's like 0.998, then it's not close to zero. If it's like 0.00.
Yeah. The thing is that that's the numerical analyst viewpoint. They want to control every operation to a fixed epsilon. But if you want to achieve some epsilon that depends on the geometry, you may have to compute to much higher precision than the epsilon. I said physical constants only need up to 8 digits to output. But to solve a problem up to 8 digits, you may need 1,000,000 digits of accuracy to solve it. Because errors cascade, right? Errors can keep growing. In a long sequence of operation, the first error is 10 digits, or say 1,000 digits correct. The next one might be 500 digits correct. And the next one might be, you keep losing digits, right? At the end of the day, you may have nonsense. You may have not even one single bit, which means you don't even know the sign of the number. Okay? So you can, go back there and increase the precision and try again. You can increase and try. You can do something like that. But you have to know what you're doing. You have to know how to do this iteration correctly. What's new? The major benefit of this is it opens up the field to many previously untouchable problems for those people who work in computational geometry, for instance. The computational geometry has a lot of great progress and ideas and beautiful results, but it's helpless against anything that's nonlinear. Because its strength is in combinatorial analysis, but it cannot do numerical things. And a lot of applications are coming up that requires nonlinear things. PDEs and things like that, even in Voronoi diagrams. And such algorithms are all practical and theoretically sound. At least that's the kind of algorithms I want to design. And the complexity is adaptive. It's not, you cannot count, it's like solving linear systems. It's not say, Gaussian elimination, n cubed number of operations. So you use fast matrix multiplication, n to the 2.35 or something like that. But it's iterative and it's adaptive. And we don't know how to analyze such complexity, but they are in practice very useful, much better than the worst case algebraic counting. So that's the nature of these kinds of algorithms. So this is a bit vague here, but I just want to give you some rough idea. So in some sense, the input that we deal with are all numerical. And numbers, like real numbers, like square root of 2, you can approximate them to any precision you want. P, let's say P is a precision, means 2 to the minus plus or minus 2 to the minus P means you have got P bits of accuracy. And P can be whatever you want, 1,000,000 or 1,000, is fine. For any P greater than 0. That's all that you can do. But you cannot say, is this equal to 0? That's not allowed. Another thing is that we have to do predicates. You always have to check whether something is true or false and then do a branch. And usually the branching is by comparing two numbers, x and y. And you say, if x greater than y, do this branch, else do that branch. But really, very often, what we say is when it fails the test, we conclude that x is less than or equal to y. But in such soft computing, you can't do that. You may have to try again at a higher precision. You really cannot. So this is sometimes called a one-sided test. Okay, you cannot. It's not a two-sided test. The failure doesn't mean it's the negation. And one way to encapsulate all these things is in what I call a soft predicate. Now, I call them soft predicates, but they're actually well defined. They're always defined with respect to something very exact. I call them hard or exact predicates. And we're going to work with intervals like I, and this is a set of all real intervals. I use a box R to indicate real intervals. And you can generalize boxes to d-dimensional boxes, B, which are d-dimensional boxes. Mostly we're going to do 2 or 3D, as in this kind of pictures. And so suppose I give you a predicate, C. For every number C, for every pair of numbers, say x, y, C will evaluate to a sign, which is usually a sign of some real number, which is 0 plus or minus 1. So, if C might be evaluating the sign of a polynomial at a point, a bivariate polynomial. And I'm not interested in computing C directly. I want to compute what I call a soft version of C, C tilde. C tilde takes not a pair of numbers, but a pair of intervals. So it's a box, a two-dimensional box. And it will give you plus minus 1. And it's a soft version if it has two properties. First, it has to be conservative. Conservative means that if C evaluated at the box is not 0, if it is not 0, it means it's either plus or minus 1. Then actually C is the correct answer. This is equal to the exact answer. Now what do I mean by this is C is evaluated at a point, but when you evaluate a box, it means every point in that box is plus, or every point in that box is a minus. Okay? It's conservative and convergent. Convergent means if you have a sequence of monotonically decreasing boxes that whose limit is a point P, then C or P is the limit of the approximation evaluated in those boxes. Of course, this limit is not too exciting kind of limit because these are just two possible values, right? And three possible values. So what it means is it stabilizes. Eventually, it will stick to some answer, the correct answer. And in fact, the only way this has a limit is that at first it is 0, 0, 0, and at some point it switched to 1, and at that point it doesn't change anymore. That's all. It must switch and calculate an answer. So I've sort of given you the groundwork, and now I want to give you a particular algorithm for Voronoi diagram, illustrating these ideas. So again, here's a box, and I'll split into 4 children. Split a box B into 4 children, and I'm interested in the midpoint of the box M, and the radius of the box, which is the distance to a corner. And if I give you 2 sets, Euclidean sets, I just want the Euclidean distance between the inf of all the Euclidean distances between pairs, the minimum distance between them. I call that the separation. And for a point P, what I call the clearance of the point P is the separation P from the input set, omega. So clearly, Voronoi diagrams is very interested in this clearance, right? And again, I take omega and split the boundary into corners or edges, because here I'm only talking about 2 dimensions. So either line segments or corner or points, that's all. And if I give you a box B, I compute a feature set, the exact feature set. So if I give you a box B and I'm trying to compute Voronoi diagram, all the features who might be closest to some point in here, they are relevant to this box. That's what I call the exact feature set. So if I have a box here, the Voronoi diagram passes through this box. So this edge is probably closest to this edge and this feature and this feature. So the feature set of this box should be this F and this G. Right? That's exact. You have to know those 2 sets. So I would like to compute this exact feature set, but I don't want to do exact things. So this is only an I want to approximate it. So instead of phi of B, I want to compute soft feature set, phi tilde of B. And phi tilde of B is just the set of features whose separation from the midpoint, I always use the midpoint as a surrogate for the box, is less than or equal to the clearance of the midpoint of the box plus twice the radius of the box. That's all. Okay? And in some sense, this is a safe version of that one. It's a superset of what you want there. So it's safe. And in some sense, you can see it's convergent also. Why? Because as R of B goes to 0, this will be equal to this. So it's safe and convergent. So this is exactly the kind of softness I want, right? So the lemma says, well, as I said already, phi tilde is a soft version of this guy. It's safe and convergent, conservative and convergent. And the other thing is very important for computation is that it's distributional in the sense of if B prime is a child of B, remember we have a box B and we split into children, 4 children. So if B prime is a child, then the soft feature set of B prime is actually contained in here. So you are distributing your features from a parent to the children. Keep distributing, okay? So it's very easy to compute because after a while the feature set of every box is not all the n features, but only a few. So it's very fast to compute this feature set. Now to compute a soft feature set, we need a clearance, right? F is in the soft feature set if the separation of F from the midpoint, which you can compute very easily, is at most clearance plus twice RB. So clearance is a global thing. It's the closest point to all the features. So you can do it in linear time by comparing to all the distances to all the features and take the minimum, right? But that would be too inefficient. But what you like to do is just, you can restrict your search to only the features which are in your parent. I think I may have messed up. I think in the previous slide, I said B prime is the child, right? Yeah, B prime is the child. And here I'm actually assuming B prime is the parent. Okay, I'm sorry. So you look at all the feature set of our parents, compute the closest distance to your midpoint, this capital B, another bar here, and take the minimum. That's the separation. And it depends, justified by the previous lemma. that is enough to search within the set. So it's very efficient. That's the bootstrap lemma. So now we have to stop. How do we stop? Remember we start with a box B0 and we're going to keep splitting, smaller, smaller, smaller. And as we split, we're going to compute the feature set at every step. When do we stop splitting? Now intuitively this is, if everything were nice in 2 dimensions, the Voronoi vertices are determined by 3 features. So if there are 3 features or less, you can stop, right? Except that if there's degeneracy, you may go on forever. There's non-termination. And then there are 2 other conditions. This one is rather special. I don't think I can go into it too much. But just to give you a hint about what that special thing is suppose you have the Voronoi, you have an edge and you have a vertex, and you have a Voronoi curve, which is a parabola, determined by this feature f and this feature g, which is a line. Now, if you have a box like that, you might have trouble if you stop subdivision at that point. Because at that point, you satisfy this condition. You have only 2 features, f and g. You say, oh, I can stop. But remember, our construction will be such that in some sense we will label, I haven't told you how I'm going to do it, but this is a peek into what I'll tell you in a short while. Every corner in some sense can be labeled by the closest feature. So this one is G, it's closest to G, right? And this is closest to G, this is closest to G, this is closest to G. And F you cannot see. And therefore you might conclude that the Voronoi curve actually doesn't pass through this through this. You'll be wrong. And later, for some reason, maybe you did split this guy, and you'll see that, oh, this is G, this is F, and therefore you introduce a vertex here, and you do a construction that represents this curve passing through that. Then this one, you draw this also, FG, but there's no connection here. You missed it. The construction is wrong. So this condition is to catch this and say if that condition holds, you're something in this kind of situation, you better split. You cannot stop. You have to keep going. All right. So just to give an intuition about what is needed. So you keep subdividing until every box satisfies those 3 predicates. I call C0, C1, C2. Right. This one is C0, C1, C2. Three conditions. So that's the subdivision phase. And the lemma says, assuming omega is non-degenerate, meaning that all Voronoi vertices are determined by by exactly 3 features, not 4 or more. I don't know if this audience is familiar with Voronoi diagrams, but in 2D, even with point sets, a degenerate Voronoi diagram happens when you have 4 points which are co-circular. So if you have 4 points like this, which lie on a circle, then the Voronoi diagram, there's a Voronoi vertex right here which is determined by these 4 things. But of course this is a degeneracy. This doesn't happen normally because in general 4 points should not lie on a circle. But if that happens, our algorithm will not terminate because we're looking for at most 3. So, and in general, you can have arbitrarily many points on the boundary. I mean, on a circle. That's a severe problem, and that's the last part of my talk, how to handle those kinds of things. Remember we have three phases. We have subdivision phase, which keeps subdividing until some soft predicate is true. I've just described the soft predicate. The second one is regularizing, which is, as I said, going to be just you look at a box and say, look at my neighbor. If my neighbor is look at my neighbors around me. If any one of them has depth that is more than my depth by 2, I have to split again, right? So it's fairly straightforward. And you do that, and that this phase will not create more than double the number of nodes leaves that you already did in the first phase. So this is a cheap phase. At most double your time in some sense. And why do we need it? So that we can do correct construction. And in some sense, you'll get a hint about that in my next slide. So remember, we have 3 phases in our algorithm. Phase 1, subdivision. Keep subdividing until the predicate C0, C1, C2 is true. And the second is regularization, which is saying keep further splitting until everything is regular, until everything is balanced, what is called balanced. And then now we construct. At that point, we have enough information to construct our Voronoi diagram. So when your feature set phi tilde of B, this has at most 3 elements. That's a condition for stopping. So it might be equal to 1, but that's not very interesting. There's no Voronoi diagram there, right? Voronoi diagram is determined by at least 2 nearest objects. So this is not interesting. 2, well, that's a bit more interesting. Potentially there's a Voronoi curve passing through it. And all that you have to do, if things are okay, you just do the label. If the 2 features are F and G, if you see F here and G here, you know that curve passes through there. The Voronoi curve passes. If you see G, then you say, so you can draw this curve. That's it. And provided we don't have this kind of funny situation, for instance. And also, what if phi tilde of B equals 3? There you potentially might have a Voronoi vertex determined by those 3 things. And you have to confirm it somehow. And here we use exact computation. I cheat here, but it's much easier to explain it that way. Here we're exploiting very special properties about this particular Voronoi diagram. That is, they are either points or line segments. And because there are only 2, either you have 2 line segments, the Voronoi edge determined by 2 line segments or 2 points are always a straight line segment. So we can draw that straight line segment and see how it cuts this curve, and then pick the other curve and see if it cuts the other curve inside this box. That's it. If it is, you have found a Voronoi vertex. Otherwise, there are no Voronoi vertices. And you can continue construction. So now you have found the Voronoi vertices. You put a Voronoi vertex in the center of every box, and you know how to connect it outside. And then you have to, these are the rules for connecting. And again, we label the corners of the boxes with either the 3 features, F, G, or H. For instance, this is H, this is F, this is F, this is G. So between G and F, there's a Voronoi, FG Voronoi edge coming in. And why is there a label in the center of the box? Because of balancing, because of regularization. Your neighbor may have split. And when your neighbor split, your neighbor introduced a vertex here. And you have to know about that sign, and so on. Right? If you don't balance it, you could have lots of neighbors, very small neighbors around, and then you go crazy. You don't know how to connect them. So balancing is very important. It's clear from this picture here. And this red bar means that this situation cannot arise, because somehow we should make sure that this doesn't arise. Because if this arises, you don't know how to connect them, because you connect them this way or you connect them that way. You don't know. have some funny connections like that. That certainly can happen if this were the